Today we want to talk about a new kind of integral. I don't know if it's new to us, a new kind of integral, a flux integral. We want to talk about what we're going to be calculating, how it fits in integration, that is. What can it represent? That's always a bigger question than we usually get into. And where's the fundamental theorem of calculus in all of this? So here are the things that we want to think about. What are we calculating? How do we go about that? What will this calculation represent? And where does the fundamental theorem of calculus show up in all of this? This being a calculus class, we should probably talk about where the fundamental theorem of calculus shows up. So in a flux integral, we are integrating a vector field, like a line integral, integrating a vector field over a surface rather than just a curve. So we are integrating a vector field over a surface. We're going to integrate a vector field over a surface. I just realized I don't remember what notation we use in this kind of book. Where is it? At one point, I noticed I was using the notation that I was raised on, and the book that we were working out of was using a different notation. Oh, we are using DA. All right, fine. And the students were like, "Oh, where is this in the book?" And I said, "It's here in the book." And I said, "No, it's not," because the notation was all different. So we're going to use DA. Cool. All right. So we're in a flux integral. I should edit that part out. It's fine. We'll integrate a vector field over a surface. We're going to integrate a vector field over a surface. So here's what we're going to write. We're going to integrate a vector field over a surface. So we're going to integrate a vector field. First of all, we're doing an integral. So we have to decide where we're going to calculate the integral. So I'm going to say integral over S. S is going to be some surface in R3. The set over which we're integrating is a surface. Specifically, we'll be putting our surface in R3. This is an integral. Our operation is going to be a multiplication. The multiplication that we're going to be using is, unsurprisingly, a dot product. Since our vector field, the function that we're integrating is a vector field, we're going to be using a dot product for the multiplication. And as usual, the D part, the small piece, is going to be a dA. That's going to be a small piece of the surface. So I need some kind of the small bits that we're going to break the surface up into. We're going to note those with a dA. Note that just like with dr in a line integral, dA is a vector. It has to be a vector because we're multiplying a vector field times this small piece of the surface. So dA is a small piece of the surface It's a small piece of the surface S, but we note that it is a vector. So it's a small piece of the surface S, like we're going to be expecting, where we're going to assume that everything is nice and constant, even though everything is continuously variable. It's a small piece of the surface S, and we also want to note that it is a vector. To make our multiplication go. So we have a surface, and I want to give a vector on that surface. In a line integral, the dr was a small tangent to the curve. But with a surface, I can't use a tangent to the curve because there's an entire plane that's tangent to the surface at any given point. So tangent is out because it's not just one vector. Unless we think of that tangent plane and describe the tangent plane with a normal vector. This is why we're restricting ourselves to R3. So the small piece of a surface S, it's also a vector. We're describing this small piece of the surface S as a vector normal to the surface. This is the setup that we're going to use for a flux integral. I've described what we're going to be doing with this. But we are evaluating. We want to integrate a vector field at a bunch of points on a surface. So we just have to make the calculation work out. Then we could think about what we can do with the calculation. So what we're imagining on the surface we imagine looking at this surface from the side, then at a particular point, I'm going to describe the surface with a vector that is normal to the surface. So we're going to think about the vector field and multiply that with a normal vector to the surface. So at each of these points, the vector field is doing something else. The vector field is doing whatever it's doing at all these points on the surface. And we're going to include the surface in the multiplication by looking at a vector normal to the surface. So those vectors dA are normal to the surface. That's going to be it does, it's not going to be any normal vector. It's going to be specifically how big that the length of it will be the size of the area. So this will be similar to when we had a curve in a lot. So in a flux integral, this is what we're dealing with. This will be similar to when we had a curve in R2 or R3. We calculated the dot product of the vector field and a tangent to the curve. So dr, these are all tangents to the curve. And the magnitude of the dr represented how often we were calculating those tangents. So if we were using this this normal over a larger area, then they're going to be larger. Think of it as the size of the dx. Correct. So as we break the surface up into more small patches, then the size of dA, the magnitude of dA will shrink. So the magnitude of the delta will be an indication of the size of the piece of the surface we're describing with that vector. So the magnitude of the dA normal vector will represent the size of the small piece of the surface S. So dA will shrink as we calculate at more points. This is similar to the vectors that we were using, the vectors that were tangent to the curve. The vectors dr got shorter the more of them we used. So just like in a line integral, the magnitude of the dr gets smaller as we break the curve into more tangents. Magnitude of those dr tangents gets smaller as we use more of them to describe the curve. In the same way, when we're finding integral of a function of one variable, dx, the dx gets smaller. So that's that shrinking part as we do the calculation more often. Those are all the elements that we need to calculate an integral. We've got some operation now we're trying to perform, usually a multiplication in which one of the factors is continuously variable. So in this case, we have a vector field that is going to be continuously variable. And we have a set that over which we're trying to evaluate. That is a continuum, just like this interval from A to B, just like the curve, which represents a path from P to Q. Here's a surface. This surface is just the set that we're in R3 that we're plugging into the calculation, the place where we're multiplying, all the different places we're multiplying. And that's what we need for an integral. Some multiplication, where one of our factors is continuously variable, and a continuum over at which to evaluate our product. Any questions? Since we're evaluating it at a surface, and since we're using a dot product, I need a vector at every point on the surface. I got a vector from the vector field. I need a vector at every point on the surface. And the vector we're going to use, since we have a surface, is going to be a normal vector. The magnitude of the normal vector will decrease as we use more normal vectors. So what can this represent? Well, we're doing a dot product, so anything that has a dot product that we can calculate with a dot product will be appropriate for this flux integral. We're imagining the vector field at all the points on the surface, so our default thinking for a flux integral is imagining a vector field flowing through some surface. All of our integrals have some kind of default thinking. Our original integral we thought of as area under a curve and above an interval. Our line integral default thinking was work is equal to force dot distance. So our default thinking here for a flux integral, we're going to imagine the vector field as the flow and the surface. We're going to imagine the vector, words are difficult. I think I need more coffee. We're going to imagine calculating the flow of the vector field through a surface. So in this case, we're imagining the vector field as a velocity field, and then the surface as just an area where we're measuring the velocity as it flows through. So we're imagining our vector field as a velocity field. So maybe our vector field is in meters per second, and our surface is some area. Say in meters squared. And so if everything is constant, I'm just going to take our velocity, and everything is in the same direction since we're thinking about dot product. If we have some constant vector field, over flowing through some surface. We are just, if everything is constant, the vector field is the same throughout the area, then what we're calculating is going to be meters per second times square meters. This will be the amount of flow that we see, the volume per second through the area. So if I take F meters per second, and everything is going in, if it's going perpendicular, we'll just multiply by the area in square meters. That will be the flow through the surface in cubic meters per second. So if we take meters per second and multiply by square meters, we'll get cubic meters per second. If everything is constant, then we get to multiply. If we see that the speed of the water through a pipe is a constant, 5 meters per second. I don't even know if that's fast. I should probably look up some speeds of things. But anyway, water is flowing through a pipe at 5 meters per second. And the pipe has an area of 10 square meters. Then we're going to be getting 50 cubic meters per second through the pipe. That's the volume that's going through the pipe. If the water is flowing perpendicular to that area, and it's constant everywhere. So if our vector field is constant at all the points on the surface and the vector field is perpendicular everywhere to the surface, then we get to multiply. That's the baseline state when things are not continuously variable. This is what integration is trying to do. Integration is multiplication when things are continuously variable. Since we are multiplying with the dot product, that means two things. Not just the same magnitude, but the same direction, perpendicular at all the points. So in a dot product, since we're multiplying vectors, constant means a couple of things. Same magnitude and same direction. For vectors, constant is going to mean the same magnitude and the same direction. Any questions? This is going to be what we're one of the things that we think of. This is why we call them flux integrals, because flux is just flow. I'm not sure why we didn't just want to call them flow integrals. I think we sound fancier if we do flux. I don't know. I missed that meeting. I wasn't there. Plus, it happened a long time ago. That's why I wasn't at the meeting. What's that? Yes. Yes, because we can imagine current as the flow. So let's just briefly take a trip and think about where the fundamental theorem of calculus, mainly because that's what we were talking about yesterday. The rest of the other parts of this, if actually before we do that, the idea with integration is that if everything is constant, then we don't have to do integration. We just get to do multiplication. We get to multiply constants. The idea is that if the vector field is different at all the points on the surface, then I've got to break the surface up into small pieces and calculate the dot products with the vector field at all the different points. When we say integration is multiplication, but one of the factors is continuously variable, that doesn't preclude both factors being continuously variable. So here, if I have a vector field that's different at all the points, maybe we should just draw another one. So if I've got a surface that's flat, it could be that the vector field comes through at different angles. So up here, maybe it just comes through perpendicular. But at different points, it's flowing at different angles. So it's coming through the surface at different angles. So we're and different magnitudes and different directions. So we're going to have to calculate the dot product of the vector field at different angles or at different points. It could also be that we have, but in this case, the surface is flat. But if we have a curved surface, if we have a curved surface, then we're going to do the same thing that we always do. We're going to make things constant in small pieces. So here, I'm going to say this little patch I'm going to describe with one vector. I'm going to grab a normal vector. And then here, I'm going to grab another patch on the surface, and I'm going to describe that patch, that whole patch, with a normal vector. And then at each of those points, I've got the vector field doing its variable thing as well. So the vector field is variable and the surface is curved. So I want to know what component of the vector field is perpendicular to the surface. In a dot product, we're going to be thinking about the component of the vector field that is perpendicular to the surface. So surface integrals show up in the fundamental theorem of calculus in Stokes' theorem and in the divergence theorem. So we have Stokes' theorem and the divergence theorem. Remember, in a fundamental theorem of calculus, we're going to integrate the derivative of some function by evaluating the function at the boundary. That's our fundamental theorem of calculus thinking. We integrate the derivative of a function over a set by evaluating the function at the boundary of the set. So one of these is the divergence theorem. So the divergence theorem says that if we want to integrate over some solid W, the divergence of a vector field at every point in that solid W. So W is going to be some solid. dV is some piece of that solid, like it is in a triple integral. And the divergence of the vector field is something that we haven't talked about. And I'm like, oh, don't worry about it for now. We're thinking about in terms of math, we're thinking about the structure, we'll worry about what's going on. Think of divergence. Think of the divergence of a vector field as how much explosion we have for the vector field, how much the vector field is pushing out. Is the vector field pushing out with some positive divergence or kind of sucking in with some negative divergence? Yesterday, I described the divergence of a vector field as the dot product of the del operator and the vector field at all the points. So this divergence of the vector field, that's acting as the derivative of the set. So here is where I'm being kind of a dick, and I'm like, oh, it's a derivative. So the divergence theorem says the following: if we integrate over some solid in R3, the divergence of a vector field at all those points, we can calculate this by integrating over the surface the vector field dot dA. So in this setup, f is the function. And S is the boundary, the surface that is the boundary of the solid W. So we have some vector field, and the divergence of the vector field is going to be telling us how much the vector field pushes out or pushes in at any given point. And we're looking at how the vector field pushes out or pushes in at all the points in some solid W. And we can calculate that by just looking at how the vector field flows through the surface of the solid. So that's how this fits the description of a fundamental theorem of calculus. We're integrating the derivative of some function over a set by evaluating the function at the boundary of the set. This is called the divergence theorem. It is one of our fundamental theorems of calculus. It's the fundamental theorem of calculus for triple integrals, maybe. How about that? They all have to have a name. Now in my mind, they all have to have a name, and they all have to have what they're the fundamental theorem of calculus for. The reason I like to bring this up now, even though it shows up in the whole second, the chapter after we talk about flux integral, is that it's giving us an idea about how we could think about flux integrals. We could think about flow through a surface, and it also gives us an idea about what this divergence is representing, the divergence of a vector field. How much of the vector field is the vector field expanding, or is the vector field contracting at any given point, and by how much?
And what is that symbol after div F?
This is del.
Del? Is that like a
It's an operator.
oh, but
It's
is
a
it like a
vector
Greek
operator.
symbol?
It's a vector of partial derivatives.
Oh. Is it supposed to be like Greek or something?
It's an upside down delta.
Oh, got it.
In a very Palmolive maneuver, we've been using it all along. If we just have a function of one variable, then instead of with partial with respect to y and partial with respect to z, we just have the derivative with respect to x, and we apply it to a function. So yeah. Yeah. So we want to think of divergence. This is something we haven't talked about. This is something we definitely haven't talked about. But we just want to think about divergence. When we're looking at a vector field, think about how much at a particular point in a vector field, is the vector field kind of representing some kind of expansion or some kind of contraction, right? So expansion, or we can have or contraction, and amounts, like it's maybe the vector field is expanding slowly. We think about the air at this point. Is it moving away fast? Is it moving away slow? Right? So that's one of the things that we could think about with divergence. It's just how much is moving away, moving towards. And this is at all the points on some solid. So imagine at all the points in this room, we're just looking at the vector field of, let's say, airflow through this room. And at all the points, the air is moving away, moving towards. And we're doing this at all the points on this solid. We can calculate that total. We can get that sum of all the stuff going on in the interior just by measuring what the vector field is doing as it flows out of the room. I know the air flowing out of the room doesn't make any sense, but we're trying to do a math problem, not a physics problem. We can calculate what's going on all throughout the interior just by looking at how the vector field flows through the surface of the solid with our surface integral. And the reason that I bring this up now is that we want to think about, later on, we're going to be thinking about divergence. And I want to think about divergence in kind of hand-wavy general terms. So functionally, all we're doing is calculating the dot product of a vector field at a bunch of points. The bunch of points in our surface integral is just a surface rather than a curve. Instead of a bunch of points from a one-dimensional curve in R3, we're calculating the vector, we're looking at the vector field at a bunch of points on a surface in R3. Normally at the end of class, I ask if there are any questions, but I'm not going to today because there are supposed to be many, many questions. Nothing is really supposed to make sense right now. Right now, if you listen to what we talked about today with flux integrals, and it's like, oh, that's all makes sense, you're incorrect. It doesn't make sense. Think about it some more until it doesn't make sense, because it's the first day of flux integrals. Nothing gets to make sense. All right, that's going to do it for today. As you walk around, look for some surfaces and think about some vector fields flowing through those surfaces. Everybody have a good day, and thanks for playing.